D is sort of the greatest one, and you have another one, what should divide what in this case? C should divide D. Okay? If D is the greatest common divisor, then every other common divisor should divide it. After having told you not to think about division, I'm using the word divide an awful lot, but right, you know that. Okay, so, right? And number 4, if C is a common divisor of A and B, now we finally get the greatest part. Then C is less than or equal to D. Okay, so the hardest thing to prove, and the thing from which everything else follows, which sort of tells you why it's important. I mean, if you just had this, right, you'd have no way of knowing that somehow you can write it in this way. So this is really the important part of this theorem. Once you got this, the rest of it's no problem. And getting that is going to be a bit of work. We will do the case when A and B are bigger than or equal to 0. Other case, well, there are two options here, okay? What you're hoping me to write down is that there is similar, but what I'm actually going to write down is an exercise, exactly. See, you guys know me pretty well by now, right? And I say in the exercise that you should not go through and imitate this. You should do the trick that we just did before, and that is we proved it in this case, and then go through the other cases. All right? Okay, so now we're going to do some cases. So first, suppose A is equal to 0. And so really what we're doing, we're going to entirely prove the first one. Except for the case there. But we're going to entirely prove this one, and then we'll show that once you have this, you can do the rest. Okay, pretty easily. Okay, so how can I find a D that's a common divisor and is a linear combination of those two? Well, we'll just let D equal to B in this case. And remember, what do you know about 0?
Its only divisor is 0.
No, it only divides 0. Okay. What are its divisors?
0.
Everything. Right? Everything divides itself in 0. So, first of all, how can I write now D as a linear combination of A and B? That's pretty easy since A is 0, right? You can write that as A times 367 plus B. Why did I pick 367? Just to annoy you, right? Okay, because A is 0, right? So it doesn't matter what I pick there, as long as it's an integer. Right? D is B, so B equals D equals that 0 plus B, okay? And B divides 0, and B divides A. Okay, so I've done this, right? I found a common divisor, and I've written it as a linear combination of A and B. And so I'm done in the case when A equals 0. So for the general case, I can assume A is less than or equal to B. So B less than or equal to A in this case is similar. In fact, since A equals 0 is done, we have what? These are both non-negative, so in fact 1 is less than or equal to A is less than or equal to B. Okay, so this is what we're going to do. We're going to prove it, in this case, 1 less than or equal to A less than or equal to B. Does everybody agree that if I can do this, then I'm finished with 1? Except, of course, for the exercise. Okay? Now, here's a concept that's at least mentioned in the text, but I haven't discussed it in here yet. We're going to use strong induction. So I don't know whether Mr. Sunkus talked about this or not. Did you? Okay, so induction works, as you now know very well, so regular induction is if P of K is true, then P of K plus 1 is true. That's the inductive step, right? You also have a base case. Strong induction is analogous to the following. If you're on let's suppose you're in a video game, okay, and you're climbing an infinitely tall ladder, right? And you're at a rung, and you need some coins or something, right? That were available on previous rungs somewhere, okay, that you have collected, okay? And those will always allow you to get to the next rung. So instead of just using the rung you're on and saying, if I'm on this rung, I can get to the next rung, you're saying, well, if I've gone all the way up through all these rungs, then I can get to the next rung. So this is a stronger version of induction in the sense that you have more that you can use, right? So instead of just being able to use P of K, you are allowed to use all the P of J's that you've already proved. Okay? And how do I prove strong induction? Well, I prove it by induction. Okay? So that it's actually equivalent. Okay? So strong induction that if P of J is true for all J less than or equal to K, then P of K plus 1 is true. The idea is that maybe there's some P of J that you've already proved on your way to getting there, and it's going to be useful for you, and not just P of K. And that's exactly what's going to happen in this proof, as you'll see. So you're now going to get a nice demonstration of how strong induction works. Okay? So now what's my variable going to be? The induction is going to be on A plus B, which I'm going to call K. So what is my P of K statement? And that is that if A plus B equals K, then the conclusion of this is true, right? So then A and B have a common divisor, D, such that what? D equals AM plus BN for some M and N in Z. Okay, so let's take a breather. I'm not sure we're going to actually make it through this, but we can make it to, I think we can get through the proof of 1, and then next time we'll talk about why these other ones are pretty easily true. Okay, does everybody understand what I'm doing? My new counter is going to be A plus B, and I'm calling that K. And we're just going to start, we're going to prove P of K for all K, right? And then I'll be done, right? Because I'll get all possible sums of A and B, whatever that sum may be, that will get me all possible A's and B's, because A and B add up to something, right? then I'm going to find this divisor. So I want to keep that statement of strong induction there. Okay, well, let's start with our base case. And for our base case, we're going to use 0. Okay, well, that means k is 0. And a and b are bigger than or equal to 0. So what does that tell us?
A and B are 0.
A equals 0, which is done. That was the case I already checked. Okay, so now let's suppose that P of j is true for all j less than or equal to k. And let a plus b equal k plus 1. Question or? So what am I trying to show? I'm trying to show that now a and b have a common divisor, right, of the form a plus n plus a times m plus b times n, where m and n are integers. So we're trying to show it has a common divisor that is a linear combination of those two. Okay, well, what I need to do is I need to have two things whose sum is k or less, right? So here's where the trickery comes in. Define c equal to b minus a. Now we're in the case where a and b are non-negative, and also we have a less than or equal to b, so what do we know about c? What is its sign? Yeah, it's bigger than or equal to 0. Okay, so this is going to be our new b. C is the new b. So now let's look at a plus c. What do we want to know about a plus c? In order to use strong induction, the sum of these two should be what? So our induction is in a plus, our induction is in the sum of the two numbers, right? And if we're going to use strong induction, that means we're going to be using P of j for all j less than or equal to k. So what would we like to know about this in order to use strong induction?
Less than or equal to k plus 1.
Yes. Well, less than or equal to not k plus 1, but if we're going to use the strong induction, we need less than or equal to what? K, all right? Well, let's write out what it is. This is a plus b minus a equals b. And so, but we know that, now since a plus b equals k plus 1, then b equals k plus 1 minus a. And what do we know about a? Is greater than or equal to 1. So what is this now? Less than or equal to k, since a is bigger than or equal to 1, because we ruled out the case a equals 0. So now you see on these two ones, this is now less than or equal to k. So I can use strong induction on the new one, a and c. So the strong induction tells me that I can find what? So I can find D such that D is a common divisor. So D divides A and D divides C. And D is a linear combination of these two, but I'm going to use different letters. So let's say RA plus SC with R and S an element of Z. But let's look at this carefully. If I replace this now, replace C again by B minus A, what do I get? RA plus S times B minus A. And how can I now rewrite this?